Thank you so much, Guy, for joining us. I'm going to ask the next speaker to turn on their video. That's Ekansh Sharma.
Hello, can you hear me?
Yes. Ekansh, why don't you take it away?
Right. Hello. So I'm going to be talking about approximations in probabilistic programs. So this is joint work with Dan Roy. So let's start with like motivation of like just probabilistic programming in general, though like everyone in the audience is probably familiar with it. That when we are doing like Bayesian modeling in any probabilistic programming system, so we ask the user to give us like some prior beliefs about the world, so which is given as like some code that represents their prior beliefs. That's how the world functions. Then like the user collects some data, and given this like prior beliefs in the data, they feed it to their favorite probabilistic programming system. So here, I'm not like choosing favorites, but like here you can pick your favorite. And the goal is that these probabilistic programming systems then hopefully tell us something about the posterior beliefs once we have observed the data. So we want to compute essentially the conditional distribution of our model parameters given that we have observed the data. So as we heard like in Guy's talk, there are like many classes of models for which like computing the posterior is tractable, and like, but they're very structured. But because probabilistic programming allows for representation of very large classes of models, so computing the true posterior for most of them is intractable. So what these probabilistic programming systems do is essentially like somehow compute an approximation. So we have like a p tilde now instead of the true posterior. So that's how they get away with like essentially like not trying to compute the true posterior. They can use like algorithms like variational inference or more like systematic approach, which is the Markov chain-based methods, where you have some sort of convergence guarantees. So first question that we're like interested in asking is like, how can we reason about these approximations? So like, how do we compare this approximate program to the original program or the true model that are like true posterior? How can we compare them? And especially this question gets even more interesting when we have composition of multiple probabilistic programs. So when you have like outputs of an approximate representation of a program fed in as input to another probabilistic program, and we'll have like these nested layers of approximations. So the goal of this work is try to answer some of these questions, which we believe is very important. So to do that formally, let me just introduce the like formal language, which is like essentially like we're going to follow the template of the language provided by Staten. And it's basically an idealized language where we have like constructs for representing probability distributions. It provides us like a language construct for a sample that essentially takes in a probability distribution. And like essentially the meaning of this sample is measured here. So you can think of it intuitively as that sample is producing a sample from this probability distribution. The language allows us to like sequence using let construct and like have case statements. So because this is a first order language, so we are not allowing for recursion, because that makes our analysis for approximations slightly easier to handle. And we can like deal with the S finite semantics that like that was proposed by Sam Staten and all. Okay, so because this is a probabilistic language and we want to represent data, so this language allows us to like input likelihood of our data, which essentially what it does is like multiplies the prior probability with the likelihood. And our goal eventually is to compute, like infer the posterior probability, which is essentially just the normalized probability measure of this representation. So this likelihood term sometimes is referred to as a score or like factor in like languages like web people. So our goal is like there are different implementations of this construct infer, and how can we reason about like a particular implementation. So for this talk, I'm going to mostly focus on these Markov chain-based methods to approximate the posterior distribution. So let's look at a very simple example. So where I can look at the like nitty-gritty details of like a compilation procedure that'll happen for a simple probabilistic program. So consider that we want to model like the bias of a loaded coin. So we have a coin, and because I'm in Canada, so I'll use 2D. So we toss this coin like n times and observe a sequence of heads and tails, and we count the number of heads and tails. And the goal is that we want to infer the posterior probability of like what is the bias of this coin. So we can represent that as a probabilistic program. Here, a priori, I don't know like what the bias of the coin is, so I set that prior to be the uniform distribution between 0 and 1. So I don't know anything about the coin, so the bias can be anything. Then I scale the likelihood by this likelihood of the Bernoulli distribution. And our goal is to compute the posterior distribution of the bias. So we just like plug it or infer, which should return the normalized posterior distribution. For this model, like computing the posterior distribution is like fairly easy because this is like a conjugate model, and I can like exactly compute the posterior distribution. But let's say we are using one of those black box probabilistic programming systems where we want to compute like an approximation of this, or like we want to use like MCMC based methods because like knowing that for this particular model there exists an exact representation is difficult a priori. So I'm gonna like here give an MCMC based compilation scheme for this program, and this like this scheme is like probably like very similar to an implementation of like some of those lightweight languages like the people or church. So like the idea is that you give an initial distribution on the space of like the bias of the coin, which is from 0, 1, and here I'm going to just like set the initial distribution to be the prior. And then we define this Metropolis-Hastings transition kernel that takes in a proposal distribution, which maps from like my current belief of the prior of the bias to like some new like for the new bias. So essentially, like I'm going to propose using like, so I'm going to set the proposal distribution to be the uniform distribution again, because like because I'm developing like an independence Metropolis-Hastings scheme. And the main detail like that goes in is like with what probability do I accept or reject this proposal? So this proposal in our example is like accepted or rejected with this particular probability, which is designed to be such that it leaves the true posterior invariant. So this like particular scheme is like how most of these probabilistic languages essentially compute like Metropolis-Hastings based approximations. So like what we want to do essentially is like once we have a definition of this Markov chain, we want to compute the stationary distribution of this Markov chain. So currently our language lacks this like computational abstraction of computing the stationary distribution. So like let's just add it to the language. So we propose this new language construct, stat, that takes as input an initial distribution T naught over the space A, or like some arbitrary space, and takes in like transition kernel T1. And essentially what the denotational semantics for stat is that stat is the distribution that leaves this transition kernel T1 invariant. So like stat is any distribution that essentially satisfies this program equation. We can write this more formally. So this is like more formal description of the stationary, but these details are not very relevant at this point. So now, given this stat construct, we can compute the true posterior. Like we can write the compilation procedure, which says that my original program posterior, essentially we can, like, using the Metropolis Hastings trick, we can compile it down to a program with stat, and where there's no like infer or likelihood. And turns out this procedure is very general. So for every program that can be represented using infer and likelihood, it can also be represented using this stat construct. So essentially, in programming languages term, the infer and likelihood constructs are eliminable. So we can eliminate them from the language while still like preserving the representation power of this language. So far, like I introduced this new language concept and removed like the old ones of infer and likelihood. So what is the advantage of like introducing this concept? So one advantage is that we can actually think, like we can reason about approximation to the stationary rather than an approximation to the normalized construct. Because if the Markov chain that we defined, or like the Markov chain defined but inside the stationary operator is ergodic, then we know that if we run this Markov chain for long enough, it'll eventually converge to something meaningful. So we can use this like idea that we can approximate the stationary distribution by running the Markov chain, or like by iterating the Markov chain. So we can like construct these approximate posteriors. So here, approximate posterior is just the k-step approximation of this simulation of the Markov chain. So for this particular example, the Markov chain is very well behaved.
Hi, Ekansh. You have about 5 minutes.
Okay, thank you. So for this particular Markov chain, the posterior distribution, this approximation converges to the true posterior distribution actually exponentially fast in the number of steps we take. So we call like these kind of Markov chains uniformly ergodic, and it's going to be like sort of useful when we like derive the actual bound. So now let's consider the more complicated example that we really wanted to study. So consider this program, this posterior 2, that takes as input this the previous approximate, like this previous posterior. So now these kind of models are very like so like a lot of models require like these nesting to be represented. For example, if you look at doubly interactable distributions, or you look at like representations for Markov random field, they require these nested inference, these nested representations to be like given in a written in a probabilistic program. So we want to study how like these approximations would function if we have like programs that are nested together. So let's just apply our approximation scheme that we like studied earlier. So this approximation to the posterior 2 is just going to be it takes in, instead of like the true posterior, it takes in the approximate posterior, and this represents some computation, and we design a new Metropolis Hastings kernel that depends on this this approximate posterior, and we want to know how close this approximate posterior 2 is going to be the program that we are interested in. So how can we reason about like this particular approximation? So it turns out, like, so we know, so like a lot of the papers study the convergence of Metropolis Hastings or like MCMC algorithms, but they don't like, but they expect that the program that they expect that we can sample exactly from the posterior of the programs that are like inside it. So like we don't expect there to be approximations in it. So we have like one answer for this class of problems. So this theorem says that if we have like set of stationary distributions, stationary terms in our program, then and all the Markov chains that are defined by these stationary terms are uniformly ergodic, then we can control the error of our approximation. And our approximation, the error, how the error is controlled is in fact additive. And locally, for each of those approximations, it's going to converge exponentially with the number of like steps we take in that approximation. So, but there's a caveat that the constants of the uniformly ergodic chains are going to vary, and they depend on the depth of the nesting. So if we go back to our previous example, so if we had the nesting of 2 such programs, then we can control the approximation error by this particular term. So like the constant C2 was the constant for the Markov chain represented by our posterior 2. So like, but this constant is scaled up essentially. But overall, in terms of asymptotically, the rate at which it's converging still depends on the number of steps I take. So yeah, so there are 2 points I'd like to make. It's like the error is like additive in the number of stationary terms, and locally the error decreases exponentially. Okay, so like finally to conclude, so there are many languages that admit composition of probabilistic programs. Currently, we have no framework that deals with how approximations flow through these programs, right? So in this work, we developed like important first step that under some assumptions show that we can reason about this error, and we can like give some bounds and control over how the error flows. But there's a large class of models for which like the assumption of uniform ergodicity is not going to be satisfied. So like to think about this, the class of models that we are considering here, like uniformly ergodic Markov chains, they are saying that these are Markov chains that are really well, that every step that these Markov chains take are taking towards the right direction. Whereas like even relaxing this assumption, like currently the answer is unknown. So like if you want to relax the uniform ergodicity assumption to geometric ergodicity, it is unknown. So yeah, I think I'm gonna like end my talk here, and thank you for listening. I can take questions.
Ekansh, thank you for the great talk. And everybody, let's thank Ekansh in chat. So we do have a couple of questions. So the first one I'll read out. The question is, what if you would like to use a different inference scheme? So not MCMC based, but for example, sequential Monte Carlo based. Yeah. Could you still remove the infer and weight constructs and replace them with stat? And what would be the interpretation of stat in this setting?
So we can replace it with stat, but then it would represent so then the computation would be performed by the stationary distribution then. So if you're not constructing Markov chains, then reducing it to stat wouldn't make much sense. But if you have some interpretations of SMC, like also like, there are some links between SMC and MCMC based algorithms. And in those cases, yeah, you would be able to kind of reduce those into like using stationary.
All right, and then one more. So when you're using when nested infer uses importance sampling, and I should say this is a question from Alexander Lev. There's a sampling scheme where computation per sample increases over time. That converges in the limit. Is there a similar algorithm for MCMC-based infer? I must admit, Alex, I don't fully understand this question, and if you want, you can unmute to clarify.
So as far as I understand, so like the question is saying that if I have like in these, if I have like nested inference and like, so where I'm like for each layer, I'm doing like approximation using like some sort of like importance sampling based approximation. Then I can like take the limit, like I can just have two limits where like there's an internal limit and an external limit. So I'll have to like, I don't know if that, the computation there is even going to be continuous because typically it is, yeah, so like you would have to make sure that you can actually swap the limits to show that, okay, when I can like change design, then I can have some control over like how the limit is converging. So that's the, so like it is, so I don't know like if that operation is even continuous in that sense. And this is true for stationary as well. So in general, like these approximations we have very little control over. And it's like pretty, like this is just the first step into this like wide range of research problems that should be answered. And we believe it's important because people want composition.
So great, thank you, Ekansh. In the interest of time, Alex, maybe I can ask you to follow up online.